Welcome to UVU CS3060 Lecture 4.4, where I discuss threading issues that need to be considered when working with threads. There are lots of different threading issues that exist, such as what should be done with threads in the case of the fork and exec system calls. How should signals be handled? Should they be synchronous, meaning that one particular thread, or asynchronous, meaning any thread can receive it? Thread cancellation. How do you terminate a thread remotely? Should that be done asynchronously, or should it wait for the thread to acknowledge the termination? Also, we need to consider thread local storage, such as the stack, as well as any scheduler activations. So, fork and exec pose a particular problem with threads. Say, for example, one thread calls fork. So which actually should happen? Should we actually just duplicate the calling thread, or should we duplicate all of the threads? Now, some Unixes have a couple of ways, allow for two different ways of doing this with two different forks. Linux, it only duplicates the calling thread. All other threads are not duplicated at that time, which, as you can imagine, may cause particular problems when it comes to sharing of memory and such. Exec is also a very interesting question. How should this work? Should it go ahead and just replace just the running process, or should it replace all threads? In the case of Linux, exec replaces all running threads in the process. So if you have 5 threads running, exec kills them all. Signals are also another interesting problem with threads. Now, a signal is used to notify the application that an event has happened. The operating system kernel can send these, and processes can send signals to other processes. Now, in a single threaded process, what happens is there's a signal handler that takes care of it from the main thread. But if we have multiple threads running, the question becomes, which thread should receive the signal? Which thread should be interrupted to handle the signal? Now, most of the signal handling that we've dealt with or that we've seen are things such as Control C. If you press Control C, you send a signal to the program that tells it to terminate. There are lots of other signals as well. If you've ever had a program crash, you may have had a segfault signal sent to your program which tells it to shut down. Now, there are two types of signal handlers. There's a default signal handler, which is created for every executable. Every time you run a program, you have a signal handler. It's called the default signal handler. So, for example, Control C would terminate your program for you via the default signal handler. We can also create user-defined signal handlers. And every signal that has a default handler that will be run by the kernel when handling it. If you create a user-defined signal handler, you can override the default signal handler. The question is, whenever you have multiple threads, a single thread just simply does the single signal to that process. But how should we manage signals that are being delivered for multi-threaded systems? Well, there's several ways to do that. We can deliver the signal to the thread to which the signal applies. You can direct a signal to a specific thread in some systems. You can deliver the signal to every thread in the process, so every thread receives the signal and handles it. You can deliver the signal to certain threads, and sometimes even random threads picked depending on which thread is available to handle it. Or you can assign a specific thread to receive all signals. Within the Linux operating system, it is a random choice as to which thread is going to handle the signal in a multi-threaded system. Normally, though, you can mask particular signals so that per thread, so that if a thread chooses not to receive a signal, it can mask that thread. Therefore, another thread will have to pick that signal up. So thread cancellation is where we terminate a thread before it is finished. And usually we have a target thread that is going to be canceled. There's two general ways of actually performing thread cancellation. We have the asynchronous cancellation, which causes the target thread to close immediately. The other option is to do a deferred cancellation, which allows the target thread to check and poll. Have I been terminated? Nope, I'm going to continue on. You can, with pthread, perform a cancellation on a particular thread. You take the thread handle and you pass that thread handle into the pthread cancel. And this is an asynchronous cancellation, meaning that particular thread will be shut down immediately. Now, depending on how you want to cancel this, whether it's going to be deferred or asynchronous, will determine how and the state of the actual thread. So if a thread is disabled, it's not really going to it's not going to perform the operation. It just waits until that thread is enabled again. A cancellation can be deferred to a cancellation point. There's a function in pthread called pthread test cancel, and the pthread test cancel will actually wait for that particular cancellation notification, which allows it to clean up after itself. Linux systems will handle cancellation through signals, and as we discussed before, there's a default signal handler for that to happen. The default signal handler causes the thread to shut down immediately. You can create a signal handler, a user-defined signal handler, that manages a cancellation. So thread local storage is a method of allowing each thread to have its own copy of a particular piece of data. You often want to use thread local storage when you don't have control over the thread creation process, like with a thread pool. This is a little bit different than how local variables work. Local variables are only during a single function invocation, whereas thread local storage is visible across function invocations. So it's like heap memory or global memory, but it is only visible to that thread. Static data is isolated between invocations of a function. So you can have a static variable that will be remembered, much like a global variable, every time the function is invocated. Thread local storage is similar, except for thread local storage is unique to each thread. Now, in scheduler activations, if you remember back to the threading models, we have many-to-many and two-level models. We have to have some form of communication to keep the number of kernel threads allocated. This is usually done through a data structure that is shared between user and kernel threads, that is known as the lightweight process. Now, this lightweight process is attached to a kernel thread, and it appears to be a virtual processor. Now, how many lightweight processes do we create? Well, what usually happens is scheduler activations provide what is called an upcall. This is communicating from the kernel to the upcall handler in the thread library, showing the thread library, hey, I need to do some work here. And this allows the application to maintain the correct number of kernel threads. This ends Lecture 4.4, where we talk about threading issues that must be dealt with when dealing with threads.